So hello, before I begin, let me thank the organizers of this conference to give me a chance to share this work here at the Bernoulli IMS One World Symposium. The title of this work is the Unified Signature Cumulant and Magnus Expansion, and it's a joint work with my PhD supervisor, Peter Fritz, and Nicolas Tapia. So let me begin by reviewing the signature. So for a d-dimensional continuous same martingale, the signature S of x is a tensor series starting with 1, and it's defined by this differential equation. So if I integrate the signature against the same martingale, obtain the signature again. And if I take a word that is a multi-index of some length n, and I hit the signature with that word, that means I look at the specific component of the tensor series, then I obtain this iterated integral of the components of the same martingale with respect to one another in this order. So if the components of the signature have finite expectation, then we define the conditional signature cumulant in this way that we take the signature on an interval from small t to capital T, we take the conditional expectation at small t, and we take the logarithm of it. And this defines the signature cumulant at small t with respect to capital T. Okay, let me give a few facts about the signature and the signature cumulant. So the signature defines an element in the free Lie group, which is embedded in the space of tensor series. The signature satisfies the chain relation. That is, if I look at the signature at 2 consecutive intervals and I multiply them, then I obtain the signature on the entire interval. Then under certain conditions of boundedness, the expected signature of a stochastic process characterizes the distribution of the signature. And therefore it also characterizes the law of the stochastic process. And now you can see that there's a correspondence between the moment generating function of a random variable and the expected signature of a stochastic process. Recently, Bonnier and Oberhauser provided a combinatorial relation to convert from the expected signature to the signature cumulant. Okay, before giving the main result of this project, I have to do a few notations. So for 2 tensor series, and the space of tensor series is now denoted by this mathcal T. We denote the tensor product just without occupying a symbol for that. And we introduce a tensor product symbol for another tensor product, which we call the outer tensor product. And then we have the multiplication map, which maps from this outer tensor to this tensor product of the 2 spaces of tensor series to the space of tensor series just by multiplying all tensors appearing in the series and then extended by linearity. And then for 2 maps mapping from the space of tensor series to the space of tensor series, we define this special product here by multiplying the 2 functions in the outer tensor space and then multiplying it and then applying the multiplication map to it. And this is what it looks like for 2 specific tensors. So now for 2 same martingales that take values in the space of tensor series, we define the outer bracket, which is the stochastic bracket of the component-wise cross variation of these same martingales, and then multiplied with the outer tensor product of the identity vectors of these components. And then we define another tensor product, which is simply the multiplication map applied to that outer bracket. And we get the inner bracket of the inner product of the identity vectors here. So note that none of these 2 brackets are commutative. Now, let me give a condition for the well-definedness of the expected signature. So this one follows from the Burkholder-Davis-Gandhi inequality for enhanced martingales. If you have this martingale decomposition of our continuous same martingale, then we have that the expectation of the signature level, of the nth signature level, is bounded by moments of the quadratic variation at the final time and moments of the one variation norm of the bounded variation path. And in particular, if we require that these two objects have finite moments of all order, we imply that the expected signatures are well defined, and also the signature cumulants are well defined. Okay, so let me now present our main result. So for a continuous same martingale satisfying the just mentioned condition, we have that the signature cumulant satisfies this functional equation. So this is an equation between of tensor series, and we have that the following, that the signature cumulant is given by the conditional expectation. And now I will go through these objects here: the increment of this same martingale, the increment of the quadratic variation of the same martingale, and now this term here is the integral of the of kappa with respect to this term, where the adjoint of kappa means the adjoint of x with respect applied to y is just the Lie bracket of x with y, so the commutator of these tensors. And the function g is defined by this power series here. Now another term is this function q of adjoint of kappa, where q is defined by this power series here applied to the outer bracket of the signature cumulant, which is a same martingale. And the final term is the cross variation of the signature applied to kappa, the cross variation of x with kappa applied to this function. Okay, I will take the rest of this talk to elaborate on this theorem. So let me look at the first two levels of the signature cumulants, with which follows from this theorem. So the first one is trivial; it's just the expectation of the increment of the martingale, and the second one is the expectation of the increment of the quadratic variation. The integral of the first level of the signature cumulant with respect to itself, and the commutated version of that integral, then the quadratic variation of the first level of the signature cumulant, and the cross variation of the signature with the first level of the signature cumulant. And this recursion proceeds in higher level, and we obtain this explicit recursion here. So we have that the levels of the signature cumulants are given in this order, that we have this term here Magnus, and I will explain in the next slides why we noted this by Mach. And we have this quadratic variation term, which depends on the quadratic variation of kappa. And we have this cross variation terms, which depend on the cross variation of x and kappa. So the time is not enough to go into more detail here, but yeah. So let me go into the boundary results of this theorem. So in the deterministic case, for a deterministic and absolutely continuous path, we have that the signature satisfies this formal differential equation. And we have also from the previous result that by this recursion that the signature cumulant is also a deterministic differentiable map, since we are in this deterministic and differentiable setting. So in this case, the quadratic variation terms of the equation 2, which I just presented, vanish, and the expectation also vanishes, and doesn't vanishes, but is redundant, and we obtain this differential equation here. So now this functional g can be inverted, and what we obtain is the Magnus expansion of the log signature, where this h functional is the inverse of g, and is given by this power series with the coefficients being the Bernoulli numbers. Okay, so finally, let me give another result that is sort of contained in this theorem. So for a given random variable that is measurable with respect to the final time, we have the final time of some underlying filter probability space. We have that the conditional multivariate cumulants of this random variable are given by the exponential, so the tensor exponential of that random variable, conditional expectation logarithm, and then applying this symmetrization map of the tensor algebra. So, and this is equivalent to the definition of this series expansion, where we have commuting coefficients in front of the components of the moments. Okay, so now for this random variable, we can define a canonical martingale by taking conditional expectations. We also have then associated to this a signature, and we also have the cumulant signature. So now symmetrizing the signature gives the exponential map, and symmetrizing the log of this expected signature then gives the multivariate cumulants of this random variable. So therefore, we have that for the first component, which is just trivially the martingale increment expectation, which is 0. For a second component, we obtain after symmetrization that we have this variation term. And we can apply our theorem, which I just presented to you, by symmetrizing. And if we do this, we obtain this theorem here, which was recently obtained by Fritz, Getherell, and Radojicic. And it's a diamond expansion for the coefficients in the cumulants of multivariate random variables. And we have that these components are given by this convolution in terms of the levels of diamond products of the components itself, where the diamond product of two same martingales is defined as the conditional expectation of the quadratic variation increment. Okay, so this result is also contained as a boundary result in this signature cumulant expansion. And let me finish my talk referring to the archive preprint, which is at the moment not available, but I hope that by the time of the discussion session, this might be available, and I'm looking forward to have this discussion. So this is the first reference slide, and this is the second reference slide. Thank you.